Our universe is not locally real. This was the thesis of the paper that won the 2022 Nobel Prize in Physics, doctored by Alan Aspect, John Coulter, and Anton Zelinger. The statement seems innocent enough, for I read up on it. It just seemed like any other scientific statement detached from me and most people's reality. But when I learned more about it, I was still right. It's still 100% completely unrelated to daily life and likely won't have any impact on me or any of the viewers watching. God damn it, it's cool! And I just want to talk about the cool thing. So, would you listen to me as I neurotically explain what it means to say the universe isn't locally real? My little PogChamp? So, what does it mean to say the universe isn't locally real? Well, reality and locality mean slightly different things in physics than they do in day to day life. Locality is the principle that stuff can only influence or interact with other stuff that's nearby. For example, I can push my dad away if he's close to me, but I can't if he's already left when I was two, when we've been no contact since the fourth grade play, where I thought I saw him. Breaking down and stopping the play and running after him wasn't enough to catch him, but I. Hmm? What? What was that? He's not coming back? Stop talking about him? Hmm. Hmm. Oh, okay. I see. What I meant to say is that I can't push someone who's a mile away. Even when two stuff, even two stuffs. What is two stuffs, dude? What did I write? Even when two things seem like they're interacting at a distance, there's actually a third thing that's moving between them. For example, when we look at Kepler 22b every Tuesday, as we all do, we can only look at it because the photons all the way over there bounced off the planet about 580 years ago, traveled through that space, and hit our eyes. Well, our telescopes, but our eyes eventually. These things are interacting locally. 22b with the photon near Kepler, and the same photon with our telescopes down on Earth. Nothing on Earth interacts directly with 22b. It's the photon that's interacting at both points and physically traveling that distance between them. In a local universe, all interactions work this way. Any effect across a distance requires something, a particle, signal, wave, etc., to travel between the objects involved at or below the speed of light. Realism is the attitude or practice of accepting a situation as it is and being prepared to deal with it accordingly. Or, as my dad always said, well, he would have said if he was here, realism is a man's philosophy. You're a man, buddy. I'm proud of you. What was that? Shut up about my dad? Yeah, fair enough. The joke's run its course. In physics, realism is the principle that objects have definite properties even when they aren't being observed or interacted with. So an apple stays green even when you're not looking at that example. Or, well, like how statues don't move even if you turn your eyes. Okay, maybe I don't really understand this. So, may have stolen an explanation off of Reddit. But hey, don't blame me. Come on, this is my fault. I don't, yeah. Anyway, here's an explanation I ripped off of Reddit. Picture two worlds, one with realism and one without. Let's say that two particles in these worlds are about to collide. Let's call them Alice and Bob. If you wanted to predict how that collision is going to affect them, you need to know their momentum. In the universe with realism, both Alice and Bob have definite momentum before the collision, meaning they have set values before they interact. When they bump into each other, they do so with those set values. The math happens and they bounce off to find other Alices or Bobs to collide with their new, definite momenta after the collision. In a universe without realism, Alice and Bob have a range of possible values. At the point of contact, when they interact, one value is decided upon for the interaction. After the collision, both particles shoot off, again existing in a range of possible values until they meet the next Alice or Bob. Maybe that seems insane. Maybe you're asking, Mr. YouTuber, are you really saying that stuff can interact with other stuff that's miles away, unrestricted by the speed of light? And that stuff doesn't have any definite properties just because other stuff isn't interacting with it? My response, dear viewer, to your very acute question is,
What? Me? Nah. No, I could no. No. Could never say that. People way smarter than me are saying that.
but don't feel bad. It's not just you, me, and our 12 IQ friends who feel this way. Physicists for nearly a century after the discovery of quantum mechanics didn't believe it either. Well, okay, maybe more like a couple dozen years, and then it took nearly a century to completely prove that quantum mechanics is true. Like, you see how that doesn't really sound as good for the narrative, right? Right? Prior to the initial stages of quantum mechanics in the 1920s, a locally real universe was the only type of universe anyone would think of. Physicists and non physicists alike believed that interactions only reveal pre existing values, rather than make objects adopt values they didn't have. Quantum mechanics, and quantum entanglement specifically, refutes this notion. Now, my understanding of the history of quantum mechanics is at about the same level as my understanding of, well, quantum mechanics. So, you know, not much. Quantum entanglement. When particles are entangled, measuring one property of one particle reveals information about the other, even if they're separated by great distances. Oh, you asked what quantum entanglement means, how it's done, and a number of other relevant and curious questions? Well, here comes the problem. If the properties of particles are undetermined until measured, and the measurements occur so far apart that no signal traveling at or below the speed of light could pass between them, how does particle A know to align its state with particle B? Now, maybe you're thinking, whoa, that's some really spooky action. Einstein sure did. And it wasn't just Einstein that thought quantum entanglement was spooky either. In 1935, Einstein, alongside Boris Podolsky and Nathan Rosen, wrote a paper hypothesizing that maybe quantum mechanics is incomplete. The universe is locally real, there's just some kind of unknown factor, a hidden variable, that predetermines these measurements. As soon as this paper was published, physicists rushed with vigor to attack quantum mechanics, searching every nook and cranny for hidden variables, desperate to be the first to find them. Or, well, that's what you would imagine would happen, right? In reality, no large attack on quantum mechanics ever happened. Physicists, in large part, just accepted quantum mechanics as is. There was no large scale search for hidden variables, and ABR's theory just didn't catch on. There were reasons for this, of course, but it is just insane that Einstein, Podolsky, and Rosen, three heavyweights in the world of physics, came up with a paper together and the scientific world just didn't care. It's like if Logan Paul, KSI, and MrBeast teamed up and put out a product and no one bought it. There are two main reasons why EPR's paradox didn't catch on. For one, quantum mechanics was incredibly accurate in mathematics. And the second reason was a paper published by John von Neumann in 1932. It was a mathematical proof ruling out hidden variables. Now, as a side note, that proof was refuted the same year as EPR's paper by a young Gret Hermann, but was completely unnoticed until almost 30 years later. Was it because she was a woman? I have no clue. I don't know. I have no idea. Maybe, though. It could be. In 1964, John Stuart Bell discovered the same flaws in von Neumann's paper as Hermann did. He then did a bunch of very cool and impressive math, I think, and showed that certain experiments could be performed to either prove or disprove the hidden variable theory entirely. And no one cared. Physicists had really grown past quantum mechanics at this point. The accuracy of its math was impossible to dispute. Bell's paper lay languished in a tiny journal in a remote corner of the world of physics. So, is that it? Does the story of quantum mechanics end with someone inventing a way to prove or disprove the reality and locality of our universe? with no one willing to test it? No, of course not. Come on. This is a YouTube video, man. I just need your retention. Thank you for being retained. In 1967, a graduate student at Columbia University, Don Closer, stumbled upon a library copy of Bell's paper. He became enthralled with the possibility of proving the hidden variable theory correct. He's different. He's special, bro. He's an alpha sigma wolf guy. Yeah, for sure. Is that appealing to the alpha sigma wolves in the audience? Hey, if you're an alpha sigma wolf, I think you should subscribe. Anyway, 3 years later, with Bell's encouragement, Clauser and another graduate student, Stuart Friedman, performed the first Bell test. Clauser had permission from his supervisors, but the problem was that they were kind of broke. Because of this, Clauser and Friedman became adept at what they call dumpster diving. Clauser's setup was a kayak-ish sized apparatus requiring really careful fine-tuning by hand that was, in parts, duct taped together. Unfortunately for Clauser and his infatuation with hidden variables, once the analysis was completed, they found strong evidence against the hidden variable theory. The result wasn't entirely conclusive, though. The equipment left a variety of loopholes in the experiment. However, reading directly from Clauser's paper here, since the results violate the inequalities, discovering systematic errors is greatly simplified. Most systematic errors are irrelevant. The detector efficiencies must depend on some as yet unknown variable. The best argument against this possibility is the excellent agreement with quantum mechanics that's been found. Nonetheless, if there's a hole, it must be filled. And if there's a loophole, it must be closed. The first attempt to close some of these loopholes was by Alan Aspect in 1976. His group's experimental results, published in 1982, only bolstered Close's results. Local hidden variables look extremely unlikely. And while this closed the gap, other loopholes still remained. In 1997, Anton Zellinger led his team to improve on Aspect's earlier work, conducting a Bell test over a then unprecedented half-a-kilometer distance. They published their results in 2015, and their results still found quantum mechanics as flawless as ever. One final loophole remained. In 2016, Zellinger and a team performed a cosmic Bell test. Using telescopes in the Canary Islands, the researchers sourced random decisions for detector settings from stars sufficiently far apart in the sky that light from one would not reach the other for hundreds of years. And, well, at this point it's somewhat unsurprising, but quantum mechanics proved triumphant. And finally, we come back to 2022, with the Nobel Prize in Physics honoring Aspect, Closer, and Zellinger. It includes an arc spanning nearly a century of scientific rigor and the need to prove without a shadow of a doubt that our universe is not locally real.